look at special sequences called geometric sequences. Here's an example of a geometric sequence. 5, 10, 20, 40, 80, 160, and so on. And you can probably see a pattern in how we get from one term to the next. If we start at 5, we multiply by 2 to get 10. Multiply by 2 again and you get 20. Multiply by 2 and you get 40, and so on. Another way of looking at that is if you take two consecutive terms and divide, you'll get the same ratio. 10 divided by 5 is 2. 20 divided by 10 is 2. 160 divided by 80 is 2. So we say this sequence has a common ratio, and we use R to represent it. Common ratio. And for this sequence, R would equal 2. Let's look at another geometric sequence. 72, 12, 2, 1/3, 1/18, 1/108, and so on. And you may be looking at that, seeing that you would need to divide by 6 to get from one term to another. An equivalent of dividing by 6 is multiplying by 1/6. So 72 times 1/6 gives you 12. Multiplying by 1/6 gives you 2. Multiplying by 1/6 gives you 1/3, and so on. So we say the common ratio here is 1/6. And go ahead and test it. Grab any two terms. I usually grab the two that seem easiest. If I know it's geometric, I would take this 2 and 12 and divide. 2 divided by 12, and you would find the ratio is 1/6. But you could grab any pair and divide, and you would find that same value. Let's look at one more. Geometric sequence 271, 27.1, and hey, let's make it negative. Positive 2.71, negative 0.271, and so on. Notice we're multiplying by negative 0.1 to get from one term to the next. In other words, if we take any two terms and divide, if you take negative, I will even write it out, negative 27.1 and divide by 271, you would find that you would get negative 0.1. So our common ratio here is negative 0.1, or negative 1/10. So let's look at a sequence in general that is arithmetic. So let me just list the terms. Did I say geometric? Terms of a sequence that are geometric. So let's let our geometric sequence be represented by the terms a sub 1, a sub 2, a sub 3, a sub 4, and continue. And we should get to the nth term, just a generic term out here. And let's talk about generating a formula for the nth term of a geometric sequence in the same way that we have a formula for the nth term of an arithmetic sequence. Well, our geometric sequence just starts with our first term of a sub 1. But remember, we would multiply by r to get to the next term. So the second term right here would be, well, let me write it a little bit better. A sub 2 is the first term multiplied by r. But then we would need to multiply this one by r again. So this term right here, the third term, could be found by taking the previous term and multiplying it by r. So we would have a sub 1 times r squared. Similarly, take that term and multiply it by r again, and we would have the fourth term is a sub 1 times r cubed. And you can see it, I can just multiply by r here, show it this way, times r, times r, times r. So to get to this fourth term from the first term, we would multiply by r cubed. Well, if we continue in that fashion, when we get to this nth term, we would start with the first term and multiply by r n minus 1 times. In other words, r would have an exponent of n minus 1. So there's our formula for the nth term of a geometric sequence. And remember, the sequence does need to be geometric in order for this formula to be valid. So let's do a problem. Here it is, given a geometric sequence with the first term equaling 3 and r equaling 2, find a sub n and a sub 7. In other words, finding a sub n means find a formula that represents the nth term, and we'll find the 7th term in this sequence. So let's just start with the formula. We know the nth term is found by starting with the first term and multiplying by r raised to the n minus 1 power. So if we substitute in what we know, we'd have the nth term is 3 times 2 raised to the n minus 1 power. And we have the formula for a sub n. Now for the 7th term, n is 7. So we have 3 times 2 to the n minus 1 power. So it will be raised to the 6th power. And of course, this exponent is always 1 less than this subscript here. So if we do the arithmetic, we'll have 3 times 2 to the 6th. Make sure you're careful with your order of operations. Exponents become before multiplication. So 2 to the 6th power is 64. So our 7th term is 192. So if we had this geometric sequence and we started with our first term here being 3, here's a second term, a third term, a fourth term, a fifth term, a sixth term, a 7th term. What we know is this term over here is equal to 192. That's what we have just determined without going through all of the intermediate terms, but you could have. Let's do another problem. Let's suppose we have a sequence that's listed this way. We were told that it was a geometric sequence, so we don't need to confirm that it is. And we're trying to find the 8th term. Well, we need the first term for the formula, and we need r. We don't know r, so let's find it. Since it's known to be a geometric, you can take any 2 consecutive terms and divide to find the common ratio. I can grab any 2. I like these 2. It looks like it would be a little easier arithmetic if I grab those 2. So I take 6, divide by 9. I'm going to reduce. So the common ratio for this problem is 2/3. So our formula for the nth term is the first term times r raised to the n minus 1 power. So if I'm looking for the 8th term, I start with the first term and I multiply by r raised to the n minus 1 power. Notice n is 8, so n minus 1 is 7. So we have an arithmetic problem to do here. So we have 81 over 4 times 128 divided by 3 to the 7th power. I actually don't even feel like figuring out what 3 to the 7th power is. I'm going to leave it as 3 to the 7th. And let's look at this 81. I know I could just grab a calculator and do the arithmetic, but I want to show you that we know 81 is 3 times 3 times 3 times 3. So it's 3 to the 4th power. Similarly, I could have left the 128 as 2 to the 7th. Maybe I'll write it that way again. And 4 is just 2 squared. So when I'm looking at the arithmetic for this particular problem, I'll look at my factors of 2. I have 7 factors of 2 in the numerator, 2 factors of 2 in the denominator. When I do the reducing, I have 5 factors of 2 left in the numerator. And in the denominator, let's see, I have 4 factors of 3 in the numerator and 7 factors of 3 in the denominator. When I do the canceling there, I will be left with just 3 factors of 3 in the denominator. And when I reduce, I have 32 over 27. And I now know the 8th term in the geometric sequence by just using this particular formula. Now the 8th term isn't too far out. You could have just gone from this term and multiplied it by 2/3, multiplied by 2/3, and found the intermediate terms until you got to the 8th term. But I wanted to show you the use for this particular formula. Let's do another problem. We know that if we're going to use a formula that requires that a sequence be geometric, we should be able to determine if a sequence is geometric. So let's look at this particular sequence. 2, -10, 50, -250, 1250, and so on. So the question is it geometric? In order for it to be geometric, there should be a common ratio. So we should be able to multiply one term by a number to get to the next term, and multiply by that same number again and again and again to get to subsequent terms. Maybe you can see it. When we're calculating the common ratio, we would take one term and divide it by the previous term. -10 divided by 2 is -5. Next two terms, 50 divided by -10 is -5. The next two terms, -250 divided by 50 is -5. And last, 1250 divided by -250 is -5. So in fact, yes, this is a geometric sequence because we have a common ratio for the problem. Let's do another one. So the question is, again, I didn't write the question again, but the question will be the same. Is the sequence geometric? Maybe I'll write that here so we know. The question, is the sequence geometric? And the sequence that we're going to be looking at is this: 1/2, 1/3, 1/4, 1/5, 1/6, and so on. So again, our test to see if it's geometric is to see if we have a common ratio. So I'll just start with the first two terms. What's the ratio when I take 1/3 and divide by 1/2? Well, we know when we have a division of fractions, we take the reciprocal of the second fraction and multiply, so it's 1/3 times 2 over 1, and we would get 2/3. Now let's take the ratio of the next two terms, the second term and the third term. 1/4 divided by a third would give us 1/4 times, we're taking the reciprocal of this one, 3/1, and the ratio this time is 3/4. And we don't need to continue because the ratios were not the same. So I don't have a common ratio, so the answer would be no here. Let's do one more. So the question again is the sequence geometric? And the sequence we're going to look at this time is 3 square root of 2, 6 square root of 2, 12, and so on. So our job is to see if we have a common ratio. So let's test it. If we take 3 square root of 2 and divide it by 3, we would just get square root of 2. Now let's look at the next two terms. We're going to take 6 divided by 3 square root of 2. Now I'm going to rationalize the denominator by multiplying by square root of 2 over square root of 2. And in doing that, I will simplify and get 6 square root of 2 in the numerator. And in the denominator, I have square root of 2 times square root of 2, which you know is 2, times 3, which is 6. Those 6's cancel, and we have the square root of 2 again. And you can continue. 6 square root of 2 divided by 6. Those cancel, and we have square root of 2. And we'll do one more pair. 12 divided by 6 square root of 2. Again, we can simplify in the same way we did this one. So we would get 12 square root of 2 in the numerator. Square root of 2 times square root of 2 is 2, times 6 is 12. The 12's cancel, and again we get the square root of 2. So in fact, we do have a common ratio for this particular sequence. So yes, it's geometric. So if we wanted, we could write the formula for the nth term. It didn't ask us to do that, but let's just practice. That means for this particular sequence, the nth term would be the first term, which is 3, multiplied by r, which we have determined to be square root of 2, raised to the n minus 1 power. So we could find any term in the sequence we like, the 5th term, the 13th term, whichever term is needed, just by using that particular formula. Let's do one more problem. And it's a little bit different. Suppose we have a geometric sequence and we know the 3rd term is 12, the 6th term is 32/9, and our task is to find a formula that represents any term of the sequence. So remember, this is what we know. Here's my sequence. This 3rd term right here is 12. There's a sub 3. And over here, this term right here is 32/9, and that's a sub 6. Remember, we need the first term and we need r in order to be able to write the equation for this. So let's see what we can do. We know that the formula for the nth term is the first term multiplied by r to the n minus 1 power. But we were given information about the 3rd term. We know the 3rd term would equal the first term times r squared. And similarly, we know about the sixth term. The sixth term we know is the first term multiplied by r to the fifth power. And let's fill in the third term and the sixth term. So for this equation right here, we know 12 equals a sub 1 r squared. And for this equation right here, we know 32/9 equals a sub 1 r to the fifth power. And now we have a system of equations that is 12 equals a sub 1 r squared, and 32/9 equals a sub 1 r to the fifth. So it's our task to find a sub 1 and r. Let's continue. And let's see, if I move this up, I think we'll have space right here. To solve this system, why don't I solve for a sub 1 in the first equation? So here's our system. Our goal is to find a sub 1 and r. So if I solve for a sub 1 in the first equation, I would have a sub 1 equals 12 divided by r squared. I'm going to make a substitution into the second equation. I'm using the substitution method here. So we're substituting this into a sub 1 in the second equation. So I have 32/9 equals, and here comes our substitution right in here, 12 over r squared times r to the fifth power. Let's do some canceling. Our r squared and our r to the fifth cancel, so we have 32/9 equals 12r cubed. It's looking a little bit better. Now I have an equation that I can solve to find r cubed. I can divide both sides by 12, or think of that as multiplying both sides by 1/12. Either way, right? Dividing by 12 is equivalent to multiplying by 1/12. And I'm doing it this way so I can do some canceling on the left-hand side a little bit easier. My 12 and my 32 have a common factor of 4. So I have 8 over 27 on the left side. Finishing solving for r, I'm going to take the cube root of both sides. And when we take the cube root of 8/27, we'll end up with 2/3. So for this particular system, we know r is 2/3. Let's finish solving the system by finding a sub 1. So 2/3 is going back into one of our equations. Let's put it in that first equation. 12 equals a sub 1 times 2/3 squared. So we have 12 equals, let's see, 2/3 squared is 4/9. We can multiply by 9 and divide by 4, or multiply by 9/4. It's your choice when you're doing the problem. Let's see, I'll just multiply by 9. Multiply this side by 9 and multiply this side by 9. So I have 108 equals 4a sub 1. And when I divide both sides by 4, I get 27. So don't lose sight of what we were trying to find. Let me bring you back. We are trying to find a formula for this geometric sequence, right? We're trying to find a sub n. And we need a sub 1 and r to do it. And notice what we have. We have a sub 1 and we have r. So our formula for the nth term is 27 times 2/3 to the n minus 1 power. So you could use this formula to find any term in this sequence that we would like. And notice, we know the first term is 27. I didn't even fill that in, but we know that now. And you could find any term you would like using this formula.